Now
words.
it's in English. I know this doesn't feel like a dinner table conversation. It's a strange dinner table with all of you there and us here. But use your imaginations. Pretend that it is a dinner table conversation with all of us talking together. Ask, question, demand, answer, and we'll have a wonderful conversation. We were thinking last night, what must be worrying you? And we thought there are two main things that worry you. What on earth do I teach first, second, and third graders, and how do I do it? And the other thing
And
that
you mustn't hit them.
Yes. The other thing that probably worries you is each of you is probably thinking, I'm the only stupid person here. I don't know any math. This is way over my head. We will fix this today and tomorrow and on Thursday and Friday. Not only will we tell you the wonderful entryways into the mathematics you already know and will know more of, but how to find, how to access more of it. But let's begin with what on earth do you teach the upcoming generation to make them members of the great civilization of the world, mathematics, which gives us the entree to the beauty of form, to the poetry of motion, to the structure of the world. So, Ellen, all yours.
For as long as there have been children, it's been considered important that you teach them how to count. There is a tribe in the jungle which doesn't know how to count. This is true. And when they go to the market, they hold out their things and say, "Give me money." And someone comes up and says, "No money," and takes their things. And so they feel this is a rather silly way to spend the day, is giving people things. Other people seem to get money. And you say, what has happened to people who don't have control of numbers? You want to have numbers be your friend. You want to have numbers be your tool. You want to have numbers which help you rather than make your stomach hurt. And I, as a child, if you said, what's 7 plus 5, would be sick. It was impossible. I could do 5 plus 5, but to do 7 plus 5, I have to take my shoes off. It's too big a number. So a friend of ours who is an Australian, and there they have the problem of children who live way, way out, not in a jungle, but in a sandy plain where there isn't even anything to count. They count grains of sand. No, it's came up with a way of teaching just simple beginning arithmetic so that it is fun and it is clear and you could never make a mistake. And it goes this way. How many boxes? 3. How many boxes could I get? Do you know what these boxes are? This box has 1, 2, 3, 4. How far? I'm going to put dots in these boxes. How many dots in the first box? I could put 1 box. I could put 2 dots. I could put what number is that? 5. Very good. You are out of the jungle. You're ready for big numbers. What number have I just written altogether? 7. No. Because what does our number system have? It has different places. Who lives in this place? 5 whats? 5 ones. 1, 2, 3, 4, 5. That's 5 ones. This is 2 whats? Think again. This is a 5, and this is a 2. What's that number? 25, because this is the tens column, and this is the ones column, and what's this? Hundreds. And I notice it gets quieter. We don't talk much about thousands. But it's pretty easy to see every box there's another 0. So we're going on, even if we don't know the word 10,000, 1 million, a billion. Children like a billion. Children like big numbers. So they say, I have a billion grains of sand. They're very proud. That's a wonderful thing to have. So, can we go further? What comes after thousands? 10,000s, then 100,000s, then... Oh, now we have an argument. Because some people have 1 million, and some people have 1,000, different languages call this different things, but we still write them all the same way. We put commas. Do you put commas? A dot. Do. So that you have a way. Oh, that's going to be hard. What's wrong with putting dots? Do I mean 10 and a half?
We use commas.
So you use commas. Good idea. Commas are much safer. Especially if you have inflation. When prices go up, you need lots of commas. Okay, so we say I'm going to have 1 here and 3 there and 7 here. What number have I? This is hard.
31,725.
You all agree, so it must be right. What are we going to do with these numbers after we have them? You're starting your first day in the new term, and your little children are in front of you, and you say, who can count? And one person says, 7, 3, 2, 6. And another person bursts into tears because she knows from her older brother that math is something that makes you cry. So you see numbers and you cry. What's the first thing you're going to do with your little children? Count. I think if you learn to count, you have a head start on what the story is. And there, the thing that's most important is to get very quickly the relationship between saying the poem and understanding the idea. I can say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then somebody says to me, what does 7 mean? No idea. It's a word. I say it. It's a song I sing. It's not something that I'm thinking about mathematically. So it helps to go very slowly at the beginning and connect not just do the reciting, but to do the thinking. So you say, what's the difference between 1 and 3? And even the littlest should say, 3 is bigger. And you start by talking about numbers. How old are you? How old is your brother? What's the difference between how old you are and how old he is? So that you're not just singing the song. I knew a little boy who could count to 100. He was very proud that he would count to 100. But if you said, what's 3 and then 4 more? He had very expressive shrugs. He was very good at going, no idea.
May I make one addition?
Did I leave out 4?
They'd like you to move to the left. One very peculiar thing, you know that we write from left to right, but we count from right to left. The larger numbers appear on the left. It's so natural to you, to us, but for little children, it's rather confusing. Why do the numbers grow bigger in that direction?
How far do you go in teaching counting? Do you count to 100? What do you think? I'm not getting. Make little quiet noises. You're the class. You talk in the class. You raise your hand. Yes.
What is the question again?
How far do you expect the first year students to count? 100? And you
50? Yeah, 10. Depends on the kids.
I would assume that very quickly everybody counts to 10 because we come with a 10 attached to us. In tropical countries, people frequently count by 20s. Why? No shoes. And, which is amazing, Eskimos count by 20. Why? Where are Eskimos? Are they counting their toes? No. Their toes would freeze. But they do count by 20 because they only do arithmetic when they're inside their houses. You don't take your mittens off, you don't take your shoes off, you go inside, and so they are a base 20 system, just the way they're base 20 systems in the tropics. But we are halfway in between, so we have 10s to count with, and we don't take our shoes off. We don't get 20s. But I think it's clear that every child should be able to count to 10 and to know the difference between 5 and 10. And I don't think it's wrong to use fingers or use dominoes or use pebbles or whatever. It's not cheating. You don't have to be abstract. You can move counters until you know. Okay, that's the first week of school. We count to 10. We all count to 10 together. We sing the song of counting to 10. And when everybody is singing the song together, we can move on and start doing arithmetic. This is a very big step. this is a hard question. You don't normally translate numbers into another language. Everybody's grandmother still does arithmetic in the language she learned when she was a child. She may have been in Brazil for 60 years, but she still counts in the language she learned as a little child. So this is 1. And what are we saying? Ones, tens, hundreds, thousands, 10,000. This is very hard for your grandmother. This is a very big number. But let's say I want to add, what should we add? What do you want to put in here? Too scary. Good question. Do we write 19 as a single number? No, we have 2 places for writing 19. So let's write 19, and we put what here? 9. And 1 there. Mm-hmm. Oh, wait. I said 19. I can't count. You see, when you're a real mathematician, you don't count. What do we want to put there? Nothing too scary. 4? Oh, 0. That's a brilliant idea. Okay. Now comes the part the children like the best. We count up. How many dots do we have in this column? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Every time there are 10, what do we do? That's the best part. When you count and you get 10, you all go, pow! Can you do that? Are you good at exploding? As a teacher, you have to do perfect explosions. They can't be too loud, they can't be too quiet. So ready, we explode. Boom. So all of these disappear, and what happens? I hear many people say you get 1 in the next. I see many people looking. That's the face you have to watch for when you're a teacher. When you see somebody who is looking, or you see somebody who is looking, that's the face you have to be talking to the next time around. Are we ready? We have nothing left here because they all exploded. But what miraculously happens? It jumps to the next box. So there is now somebody in this box. And how many do we have all together? 4. Notice that one of the great things about this is you don't have to be good at writing numbers yet. You can be doing arithmetic just with dots, which explode. And so if you can't remember what 17 looks like, you can count. And knowing how to count is the basis of arithmetic. And knowing that counting always goes the same way. And if somebody says, I am at 97, what's next? Reason says 98, because it's still the same numbers over and over again. All right, what have we here? And what have we here? And what have we here? This is a very big number for very small children. Small children like big numbers. How many candies are you going to eat? 5,000. That's power. You have these enormous numbers. Now, what we have not done much of is the exploding part. Because I thought you might be frightened if the bangs are too big. Are we ready? What do we have here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. What happens when there are 10? Very good. Good exploders. But that's a very sophisticated explosion. Could you do your explosion for the others? I tend to go things like that, but that's very North American. Okay, we have 9 and 1 makes 10. What happens when we have 10? There we go. And nobody is left. They've all blown up. But when they've all blown up, where do they go? Into the next box. How many do we have in this box now? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. What's going to happen? It's going to explode, but what's left? 1. These have all blown up, and there's nobody left but 1. And how many are over here? And now it gets easy. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, and 1. And look what's happened. Right away, without any work on have we memorized the names of the numbers, or do we know what comes after 217? You have first something that makes a nice explosion, and people like making little explosions. We have different kinds of explosions. We were teaching a class in Germany, and they were very well behaved. They all sat very quietly. They all stared straight ahead. They didn't listen to anything we said. They just sat there like this. And then we started exploding, and they looked around like, are you allowed to do this? Are you allowed to make a noise in class? And they went wild, and they were saying, can we add bigger numbers? Can we multiply? Can we divide? And you say, this is not your usual math class. You know, when you stand in the front of a math class and you look, you do not see smiling faces. You tend to see worried faces, or bored faces, or it must be lunchtime soon faces. But with the exploding dots, you can add, exercise, invent subtraction. How would you do subtraction with exploding dots? I leave this as an exercise. You invent how to do subtraction, and we'll see what happens. I'll talk to you later. Shall I go sit down?
This is just review. Give me a 3-digit number.
113.
Did you say?
Yes.
You're sure that's what you said?
Yes.
100, 110, and a 3.
Yes.
You just said it in a strange way. You said 113, but you meant 110, 3. Very. Give me a 3-digit number.
431.
Bigger.
999.
Wonderful, thank you. Did you say that? Okay. You're so quiet. Oh, good. What boom did you have in mind? Yes, say it, say it.
Boom, boom, boom.
I heard the boom. The boom was very clear, but I'm not sure what exploded.
The ones.
Which?
The ones.
Something in the ones column exploded. How many?
10.
Say it again.
10.
10. Which 10?
You can choose.
It doesn't matter. Which 10 would you like?
The top ones.
The top ones. 1, 2, 3, 4, 5, 6, 7, 8, 9. Do I have this right? 1, 2, 3, 4, 5, 6, 7, 8, 9. No. I need one more, don't I? Is that right?
Yes.
Okay. They've disappeared and? Now what? Which boom? Which, how many explode?
10.
Which 10? Does it matter? Doesn't matter. Which 10 would you like?
I don't understand.
Somehow or other, 10 of these are going to get together. They're bad kids. They're going to get together and they're going to have a firecracker. But which 10? Well, this one has a funny eye, and that one's got a strange eyebrow. And maybe this is the pal of the bad kids. I don't know. Which particular 10 would you like to clump together, get together? Someone help me, tell me.
I'd like to leave alone only the top one.
Always, oh, you're very systematic. Always do the top ones. 1, 2, 3, 4,
No, I'd like to leave alone the top one.
Leave alone the top ones, even better. Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9. Which one shall I take away?
The most higher one.
That's, I guess, the highest one. So these 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. What's left? What else has happened? Next.
Come on.
Something, this is going to bother the kids because we've stopped dead there. So, my choice would be to ask them first what happens, and then to try to take care of what happens. What happens?
Explode.
Which 10 get together? Should we always leave the top ones?
in the middle.
Middle.
Yes.
1, 2, 3, 4, 5, 6, 7. I've got to go down or up.
You know
there's 9 together, and the one in the middle column, leave the one right in the middle.
Leave that one.
Yes,
Oh,
leave that one.
wonderful. Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Terrific.
Yes. Thank you.
Everything's fine so far. But I've got to do something. Not sure what this column is. It's going to start with a 1 and have how many? I'm talking to first graders. How many zeros after it? No zeros. 1 0. 2 zeros. 3 zeros. And that's where that dot appeared. And the answer seems to be that. If you'd like to check, oh, it worked. They will love this. Do a lot of examples. Somebody, when Ellen was doing this, suggested a 0 in the middle somewhere, which is great because it's confusing and you have to make sure you're able to deal with those things. Terrific. You are now experts at explosions, at addition, and tonight you will invent how to subtract. And we now go on to the other thing we thought would worry you. You probably feel you just don't know enough math to be able to teach even first graders, because to teach first, second, third graders arithmetic, it would probably be good if you knew addition and subtraction and multiplication and division and maybe taking square roots and maybe raising to powers and maybe some algebra and maybe some calculus. Who knows how much math do you have to know to teach the fundamentals of math? Well, there's a world of math. None of us knows very much. We are very ignorant. But we have the amazing capacity to learn. And there are resources out there. There's Wikipedia. I'm sure you all know this. If you go online and go to Wikipedia and type in whatever you're worried about, what is the quadratic equation? How do you raise powers to powers? You name the question, you'll probably get the answer. There is no entry with this heading, but try such, and you begin to hunt. You can always ask a friend. You can always look in a book. You could always invent it for yourself, which is the best. You may not get it perfectly right the first time, but it'll be yours. You'll own it. We said yesterday that mathematics is about the imagination. Imagining your students, imagining forms, shapes, numbers, and how they act with one another. So this is now going to be something which I think you don't know, and we're and learn together and invent. We'll begin by inventing it, and then we'll look back on it and say, it was there all the time, and we discovered it. Different sizes of infinity. Oh good, you're looking horrified. Or excited, which is even better. How could there possibly be different sizes of infinity? What is infinity? Is it a number? Some people count 1, 2, 3, 4, 5, 10 million, 10 trillion, infinity. And you say to small children, well, sounds right, but I don't think infinity is a number. It doesn't behave like other numbers. So how could you possibly talk about different sizes of it? Well, the tribe that Ellen talked about doesn't know how to count at all. Or that Mark told me about yesterday, the Maoris, or some tribe in New Zealand or Australia that can't count beyond one. There's one and then there's many. That's the way we are with the infinite. We can count 1,112 perfectly well. We did a good job of it. But how could there be infinity? It's just a mess out there. We are to the infinite the way those Amazonian tribesmen are to counting numbers. We're very ignorant. Nevertheless, we can, and today, and right now, we will begin to come to grips with different sizes of infinity. And by the time you leave on Friday, you will know and be able to explain to others, to your grandmothers or to your students, about at least 2 different sizes of the infinite. And the counting numbers, all the counting numbers, all of them, is the smallest size of the infinite. I mean, this is just mind-boggling. Okay, what does it take to understand this? Almost nothing. In fact, could you please, without counting, you're allowed to look around, however, just tell me, what are there more of in this room, people or chairs?
Chairs.
Why? Why chairs?
They're empty chairs.
Because there are empty chairs. In other words, you have all the people who are already sitting down, then you take the 1, 2, 3, 4, 5 of us who are standing, pretend, use your imaginations, pretend that we are now sitting down in some of those chairs at the back. Oh, and then there are still some empty chairs left over without counting. I've no idea how many people there are in this room, but like you, I'm convinced that there are more chairs than people. What have you done? You've made a 1-to-1 matchup between people and chairs, or you tried to, and it failed. You made a 1-to-1 matchup between all the people and some of the chairs, and there were some chairs left over. So there must be more chairs than people, although we don't know what that number is. But we still know something about it. It's bigger. We are Amazonian tribesmen who have discovered a bigger size than the size of the tribe. Okay. So now let's do that with numbers. Take the counting numbers. 1, 2, 3, 4, you know what I mean, 5, and so on forever. Think of them, how would you like to think of them? In a row or coming in through a door? What about that? You have a room with 2 doors. There's the door back there, and let's pretend there's a door here. The counting numbers are going to come in through the door at the back of the room. First comes in 1, and then 2, you know what I mean. Through the other door, at the same time, come in the even numbers. 2, 4, 6, 8, and so on forever. Which are there more of?
Sorry, what did you ask?
Sorry?
What did you ask? I'm sorry.
Good. That's the right question. What did I ask? I asked something very mysterious. Which are there more of? Does that make sense? Counting numbers, all of the counting numbers, or even numbers? Let me help a little bit, but my help is going to be misleading. The counting numbers, and so on, that means forever. Or the even numbers. And so on forever. Which set is bigger, the top set or the bottom set?
Same size.
Same size? What's your proof?
Because they're both keep on going.
Well,
Forever.
that's a nice answer. They both keep on going. But that is an Amazonian tribesman answer. There are lots of both. But maybe there's lots more of one than of the other, although there are lots of both. Both are lots. Both are infinite. But maybe one infinite is bigger than the other. The first one is bigger. Why?
I don't know. It's bigger.
Good. You feel, it just feels right that there are more of these than there are of those.
Yeah, I think one is inside the other. So.
One is because one is inside the other.
Yes.
The second set, the even numbers, I'll call them E for even. And I'll call these N for natural numbers. The even numbers are inside the natural numbers. The number of people in this room is inside the number of chairs in this room. So there are fewer people than chairs. Of course, I do have dot, dot, dot going on here, and dot, dot, dot going on
But
here.
every number of the first set has a double.
Yes.
That's wonderful. Every number of the first set has a double. Now listen to what you said. You just said something quite amazing. You said something which contradicts what you said. I think you're telling me that there are exactly as many of each. Could you make the even numbers sit down in those chairs and
Yes.
see what's left over? Where do you want the even number 2 to sit?
Over one.
Yes, even number 2 sits in chair 1. Even number 4, even number 6. Who's sitting in chair 5? You're getting a perfect matchup between the two sets, even though one is inside the other. Now this is very, very strange. One proper subset of the other. One set is inside the other, and yet there are exactly as many evens as there are natural numbers because you made a one-to-one matchup. And made is the key verb. You constructed, you made a way of matching them up. You didn't say, well, I think it might be, or I hope it would be, or maybe it isn't. You actually told me how to do it. What does the even number 240 match up with? 100, and say it again? 123. Who's sitting in chair 1000? Even number 2000. This works. Both sets are infinite. Both sets go on forever. And yet one is a subset of the other. So therefore the infinite behaves in a very strange way. We have to recognize that we're now way out there. We're doing something which humans didn't know about 150 years ago. Galileo, the great Galileo, writes in his book, Two New Sciences, if I think about the squares of numbers, 1, 4, 9, 16, there seem to be as many squares of numbers as there are numbers, because each number has its square. And yet, the squares of numbers are so thin on the ground that you keep skipping. And then he says, I don't want to think about this. It's just too strange. It's just too hard. And it wasn't until 1870, just a little more than 140 years ago, that someone, a German named Cantor, said, I want to think about it. And his colleague said, well, go somewhere else and think about it, please, and don't tell us. And he was a professional mathematician, and he was excluded from the community of mathematicians because what he said was so, it hurt the head. But he went on thinking about it. There are exactly, yes?
Can you explain again, because I'm not understanding the real, I cannot say, sentido.
Meaning.
The meaning of this exercise.
So say it again. It's a very good question.
Explain again.
Okay.
The meaning of size.
The meaning of size. Oh, that's the question. What does size mean? This bunch of numbers, the even numbers, is, as you said, a subset. It's inside this set. This set is, in some sense, smaller than this set. Every even number is inside the natural numbers, but not every natural number is an even number. So there must be more of these. But miraculously, you found a way of pairing them up. Pairing up. So, despite appearances, although this set appears a bigger size, they're the same size. So there's something wrong with our understanding of size. Size turns out to be subtler, stranger than we thought. And it's only going to get stranger as we go on. Nevertheless, you're going to understand it perfectly. You're going to be masters of this. Let's take, not the even numbers, let's take the odd numbers. Which are there more of? The counting numbers or the odd numbers? I hear a general murmur of, which I think is saying the same thing, but my Portuguese isn't good enough to sort out mumbles in Portuguese. What are you saying? More of the natural numbers than the odds, or?
The same.
Same. And if it's the same, it's because you can match them up. How do you match them up? What do you match up the odd number 3 with?
What?
What natural number would you like to match up 3 with?
2, like
With
you
2.
did.
There it is, with 2. And 5?
With 3.
And 1? 1. By the way, with the even numbers, you matched up the even number 2n with the counting number n. Yes? With the odd numbers, it's just a little more complicated. Mm-hmm. You match up with the counting number n, you match up the odd number 2n minus 1. Good, great. There are exactly as many odd numbers as there are counting numbers. You take all the natural numbers, you break them up into boys and girls, evens and odds. Each group now has exactly as many things in it as the entire set they came from. Euclid and Greek philosophers said the whole is greater than any of its parts. Not true. The whole is equal to some of its parts. What's your favorite whole number?
My favorite?
Yes.
7.
7. Good. That's mine also. Let's take multiples of 7. This is only a little bit challenging. How many multiples of 7 are there compared to the counting numbers? I mean, we're leaving out so many in between each. We're leaving out 6 numbers here and 6 numbers here. There seem to be very few multiples of 7 compared to the counting numbers. Or what? Give me the matchup.
7 and for each n.
Yes?
The multiple of 7 is 7n.
Match up the natural number n with the multiple of 7, 7n. 1 goes with 7, 2 goes with 14, 3 goes with 21. There are exactly as many multiples of 7 as there are counting numbers. Yes, Daniela.
Sorry, you said that we go forever in this first line and the second line also forever. But how could I know how do I know that forever doesn't end? And if I don't know it ends or not, how can I say if the first ends before the other?
Great question. I think that 700 is the last of the multiples of 7, that there are no more after that. Am I right? Oh, what comes after 700? Well, I was close. So there's no last multiple of 7, because every time I think I've got the last one, I can add 7 more to it. Exploding dots shows me how to add 7 more. I think that 10 trillion is the last counting number. There's just nothing beyond 10 trillion. Except for, 10 trillion and 1. Well, I was close. Because the numbers are peculiar, you can always add 1 more. Each of these sequences goes on forever. And as they go on, you come along with your little handshaking and have them shake hands this way, and they get paired up beautifully. You think of the natural numbers walking in through the back door. You think of the multiples of 7 walking in through that door. As they come in, they shake hands. It's like the end of a football match where the rival teams nevertheless shake hands. There are exactly as many members of one team as the other. There are exactly as many multiples of 7 as there are counting numbers. There are exactly as many multiples of 1 trillion. So this is very strange. What's even stranger is that I promised to show you different sizes of infinity, and yet I'm showing you that they all seem to be the same size. I'm contradicting what I promised, but that's because this is Tuesday. By the time we get to Friday, you will be so astounded when we find a set that's bigger than the counting numbers, that you cannot match up with the counting numbers. Daniela.
What is the meaning of infinity?
I think that's the question we're answering slowly, and I think the answer is going to be extremely peculiar. Certainly on the way to that answer, this is only 2013. We're only about 140 years after Cantor did his work. People are working on this today, these ideas. We don't really understand it, but we're understanding a little more about it. We understand, 1, an infinite set has no end. It goes on forever. 2, even so, a smaller part of it has as many things in it as the big set. Already that is astounding. And that's just the beginning of our understanding. Let's go on. Let's go on to the next step. I said that the natural numbers go on forever. Well, they go on forever to the right, but they stop dead there. Give me a set which goes on forever both ways.
Integers.
Integers. I'm going to write down the integers. I'm going to write down all except one of the integers. 1 minus 1. 2 minus 2. 3 minus 3. And so on forever to the right, but also so on forever to the left. What's the next question? Which set is bigger?
the same.
Same size?
No, you cannot match.
Ah, so you can't match.
No, the other there.
You're saying this. Yeah, wonderful. We have mathematics. We have a disagreement. Can you or can't you make a match between the top set and the bottom? How? Go on.
The even numbers with the negative.
Oh, that's wonderful. You're making use of what we just did to match up the even numbers here with the positives, match up the odd numbers here with the negatives, match up even number 2 with 1, 4 with 2, 6 with 3, match up 1 with negative 1, 3 with negative 2, 5 with negative 3, and so on forever. Fantastic. A set that goes on forever to the right and a set that goes on forever to the right and to the left are the same size, the same infinity. But now let me mess it up. I left out one integer. Now, can you make a one-to-one matchup, or have we destroyed this beautiful symmetry?
And if I, like a child, say for you that my sequence is 1, 4, 6, it will be more bigger than the natural.
So more integers than naturals
Yeah.
because of this extra 0 that I threw in. What do you think? Maybe? You're shaking your head no. I'm seeing some tentative nods yes. Yes.
You could add the 0 as a positive number. Count 0 like he was positive.
Okay.
And he was positive.
What do you want to match 0 up with? 2? Good. Oh, because 0 is an even number in effect. So match up 0 with 2, 1 with 4. You're just shifting over like 1 unit, leaving the odds and the negatives alone, but just shifting 1 to the right. Okay. 6 with 2, and so on. 1 goes back to negative 1, 3 goes back to negative 2, 5 goes back to negative 3. If the children this afternoon were to walk in at this point, they would run screaming from the room. Look how far you've advanced. What has this been? Half an hour at most? Maybe 40 minutes? And we've already found something very strange, unintuitive. Daniela.
Don't you have one number, like have plus one number on the even, like 2, and 0 is one more. If I count in 2, minus 1, minus 2, I'm just leaving one number. I'm missing one. Because it's symmetrical, like here I have 1, 2, 3, 4, 3, 4, and you have the 0 that doesn't go. You should have split in half.
Yes, but Diego's suggestion was, that's okay. You're just going to take what you did before and shift one of the groups 1 to the right, leave the other alone. We could have shifted both. I could have thrown in, here, let me give you a new set. A new set, it's going to have in it all the integers, negative 3, negative 2, negative 1, and 1, and 2, and 3, and 4, and so on forever, and 0, and the letter A. Now which set has more things in it? The same. Shift, as Jago did, the right-hand positive numbers over by 1 to make room for 0. Shift the left-hand negative numbers over by 1 to make room for the letter A. Throw in some more junk. Keep adding stuff and just shift. This one-to-one pairing, this matching up of people with chairs, People, as you know, there's going to be an infinite supply of them. What are we at, 7 billion by now? And chairs, I'll bet the chair manufacturers can keep supplying chairs for them. So this shifting left and right by 1 unit is all right. Well, I can think it. I can imagine it. Now let me give you a set which clearly has more things in it than the counting numbers. And those from Fortaleza will know what set is coming up. Here are the counting numbers. All of a sudden, when I write these familiar numbers, you see how strange they are. They have strange properties that you hadn't expected. Now here's the set I wonder about. A new set, does it have more things in it than the naturals, than the counting numbers, or the same number, or fewer? The positive rational numbers. Between 0 and 1, there are so many of these, there are going to be, well, as they say, an infinite number. And that's just between 0 and 1. Go on like that. Clearly, there are more rational numbers. Numbers of the form a over b, where a and b are both positive natural numbers. There must be more of them, yes? No? Why not? Just because everything I say is false?
I think that there's a way of counting them too.
Wonderful. You have the optimism of a mathematician. There must be a way. I don't know what it is, but there must be a way. What makes you think so?
Because they're, I don't know, maybe we can build them.
Good.
I think.
Maybe we can build
All.
all. Okay, let me write them all down. Give me a few minutes to write down all the positive rational numbers. Here goes. My first row goes on, as they say, forever. You know what comes next. You know how it goes on. My second row, the first row had all denominators 1. My second row will have all denominators 2. Third row has all denominators. Good. The first column has all numerators 1, 1 over 1, 1 over 2, 1 over 3, 1 over 4, 1 over 5, and so on forever. Second row, 2 over 1, 2 over 2, 2 over 3, 2 over 4, 2 over 5, and so on forever. Let me just do one more. I know you get the idea, but you'll see why I want to oblige you. Will 17/19 appear here somewhere? Where? Yes. And yes. Which row? 17/19. Which row will it be in? 19th row, 17th column. Great. So all the positive rationals will be here somewhere. Now, as you said, let's count them. This is going to be weird, strange, notice what you're thinking, but especially what you're feeling right now. You're feeling, this is impossible. This will be so hard that I won't understand it. 10 minutes from now, you'll say, God, this was so obvious. I've known it all my life. But you didn't know it all your life. You don't know it right now, but you will. What's so peculiar about mathematics is that before you understand it, it seems so hard. And after you understand it, it's so obvious. It's what the great German philosopher Kant called the synthetic a priori. It's synthetic. It's something we make, but it's a priori. It's prior to our experience. How could it be before our experience and yet we invent it? It's a mystery. Okay, count, please. Count, i.e. tell me the first, the second, the third. Mess around, play around with it. Make mistakes.
Can match
Say it again.
the
Yes.
the even numbers with all the numerators of the
Match the even numbers, the counting numbers, with the numerators.
And
So
then
match, that's a great idea. Match 2 with,
all the numerators. 1.
I want a 1-to-1 matchup.
Yes.
I want 2 to go to only one of the rationals.
2 with 1.
So match 2 with 1 over 1. What are you thinking?
1 over 1, 1 over 2,
Yes, we've got 1 over 2.
next
Interesting.
2,
Troublesome. A suggestion. I mentioned this to the Fortaleza crew when I was very little. I'll bet this was true of you too. I hated cleaning my room. And my mother said, just start in a corner and all will be well. Just start in a corner and all will be well.
Squares.
What do you mean?
You put a square right on the 1 over 1,
So match up 1 over 1 with 1.
and then you grow the square, and you match the others.
Grow
as-
the square. That's beautiful. You're going to expand from that corner. So I'm going to make a list over here. These are the counting numbers. And I'm going to write down the matchups. 1 goes, the natural number 1 goes with the rational number, the fraction, 1 over 1. What does 2 go with? You're right, you have a choice. Because it's a square. Your choice. What would you like?
1 over 2.
Good. And then do 2, match it up with 1 over 2. Now what?
2 over 2.
Now match up the third number with 2 over 2. And then?
2 over 1.
And then go up, and you've almost finished your square. 4 is going to match up with 2 over 1.
Now you grow the square again, and you had another choice.
What do you want 5 to match up with?
I think it's closer 3 over 1.
It's a funny square.
Could be 1 over 3.
Your square looks like this. Something is begging to be matched up. Yes?
I think there's a problem. I think you have to take away the numbers where the numerator and denominator are not coprimes.
I think what you're saying is very good. I'm not sure I understand it completely. Say it again.
I think you have to take away the numbers
Yes?
where the numerador
You have to take away the numbers where the numerator
and
is...
denominator are not coprimes because they are going to repeat.
Oh, you're absolutely right. But that is going to come up in 1 minute and 19 seconds. That's a very fine adjustment. I just want to get Diego's squares finished, because I have an open square here. And then I promise you we'll do yours. Where do you go from here? Where? 3/1? Someone is feeling left out. That was an interesting hand gesture, what you did. Do that again. We've gone one, dum, dum. I agree that is a square. Okay, look, I'm happy with it. I'm happy with it. That's perfectly fine. We've got this. We've got this square, and now the question is, where next? I think you suggested 3/1 next. So sort of on to the next bigger square. On to this, then this, then this, is this right? And then this, and then this. But you're pointing out that we've counted some things twice.
Yes.
2/2 is 1/1 in disguise. Fine. You are a bus driver in Porto Alegre. These are your bus stops. And you're going to pick up people at these stops. But that bus stop, just go right through it. If you come to a stop you've already been to, just drive through it. So don't make this one 2/2. It's it's a refinement. Make it. And then on to 3/1. And that's new. That's not new. We've counted that.
3/3 it's not the same thing of 1/1 and 2/2.
Yes, in fact,
We have a diagonal.
we have a diagonal. That whole diagonal, we've already counted once. Forget it from now on. There'll be other things to forget. 2/4 is on a new diagonal. We've already counted it as 1/2. Terrific.
Yeah.
Let's end at this point, but this is just the beginning. You've already done 3 of the most sophisticated mental moves known to mankind. You've seen that 2 different seeming infinite sets are the same size. The naturals and the subset of the evens, or the subset of the odds. The naturals and the integers, one of which, the second, seems so much bigger than the first, and yet they're the same size. Then you take the positive, just the positive, rationals, and you see that by a very clever kind of zigzag counting, you're going to be able to count them too, as long as you're careful not to repeat. And there are exactly as many rationals, no more, no fewer positive rationals, as there were counting numbers. Tomorrow, positive and negative rationals. It will take no work. You've already done it. You have the idea for it ready to roll. And then we'll go on to a set which you cannot count, which has more things in it than there are counting numbers. Amazing, bizarre though that seems. Mathematics is imagination. Mathematics is the art of the infinite. By the way, you'll find all this explained in our book called The Art of the Infinite, but also on Wikipedia, online. And if you don't like the explanation, it's because it isn't good enough, it isn't clear enough for you. Make it clearer for yourself, or look for another explanation, or talk about it with a friend. You're fantastic. You're going to be superb teachers. Thanks a lot.